Testing audio check. Audio check. I think our audio has been checked. Howdy, howdy. Bing bong. Bing bong. Bing bong. Bong, bing, bing, bong. Who just DM'd me? Or who are you? All right, y'all, we will be starting in just a bit. Make sure to stick around. This one should be a good one. It might be a long one because it's an 18-page paper. However, it's about the simulation hypothesis, and people are very, very curious about it, so we may as well do, we may as well actually read the whole thing. Because, we might learn something interesting. Maybe it's... Well, welcome all. I know some of you guys would currently might prefer to be listening to debates, but don't you want to know about how we know we're not in a simulation? That's certainly worth thinking about, right? Anyway, just let a few more people stream in and then we'll get started. Have my water bottle all filled up with glorious water. Discord? Yeah, who would be able to afford all that RAM? Right, all right, let's get started. So, today we're reviewing a paper that came out 4 days ago by Franco Vazza, who is in Italy, entitled Astrophysical Constraints. Astrophysical Constraints on the Simulation Hypothesis for This Universe. Why it is nearly impossible that we live in a simulation. Great. We assess how physically realistic, let's read the abstract. We assess how physically realistic the simulation hypothesis for this universe is based on physical constraints arising from the link between information and energy and unknown astrophysical constraints. We investigate 3 cases: the simulation of the entire visible universe, the simulation of Earth only, or a low-resolution simulation of Earth compatible with high-energy neutrino observations. In all cases, the amount of energy or power required by any version of the simulation hypothesis are entirely incompatible with physics, or literally astronomically large, even in the lowest resolution case. Only universes with very different physical properties can produce some version of this universe as a simulation. On the other hand, our results show that this is just impossible, that it is just impossible that this universe is simulated by a universe sharing the same properties regardless of technological advancements of the far future. Right. So this is for all of you Phil bros out there who say, but God, simulation, we have science. We can do science, right? So the simulation hypothesis is a radical and thought-provoking idea with ancient and noble philosophical roots, mentioning Descartes and Burke. Imagine citing Descartes in a physics paper. Imagine citing a nearly 400-year-old publication. And frequent echoes in modern literature, which postulates that the reality we perceive is the creation of a computer program. The modern version of the debate is usually referred to an influential article by Bostrom. I'm familiar with that article, although several co-eval science fiction movies contributed to making this theme extremely popular. Despite its immense popularity, this topic has been rarely investigated in a scientific way, also because at first sight it might seem to be entirely out of the boundaries of falsifiability and hence relegated to social media buzz and noise. True. A remarkable exception is the work by Bean et al., who investigated the potentially observable consequences of the simulation hypothesis by exploring the particular case of a cubic spacetime lattice. They found that the most stringent bound on the inverse lattice spacing of the universe is 10 to the minus 11 GeV to the minus 1. That's a length unit, by the way, derived from the high-energy cutoff of the cosmic ray spectrum. Interestingly, they proposed that the simulation hypothesis can be tested through the distributions of arrival direction of the highest energy cosmic rays through the detection of a degree of rotational symmetry breaking associated with the structure of the underlying lattice. So what they studied was basically, if the universe is on a grid system, then they can figure out how rotationally symmetric the grid system has to be based off of the direction of high energy cosmic rays. Our work will also use ultra high energy cosmic rays and neutrinos to put constraints on the simulation hypothesis, even if in a totally different way. Our starting point is that information is physical, and hence any numerical computation requires a certain amount of power, energy, computing time, and the laws of physics can clearly tell us what is possible to simulate and under what conditions. We can use these simple concepts to assess the physical plausibility or impossibility of a simulation reproducing the universe we live within, and even of some low-resolution version of it. It's kind of neat. Moreover, the powerful physical nature of information processing allows us to even sketch the properties that any other universe simulating us must have in order for the simulation to be feasible. Neat. This paper is organized as follows. Section 2 presents the quantitative framework we will use to guess the information and energy budget of simulations. Section 3 will present our results for different cases of the simulation hypothesis. And Section 4 will critically assess some of the open issues in our treatment. Our conclusions are finally summarized in Section 5. So, that's basically the summary, or the introduction. Basically, they're going to try to use physics to try to constrain the simulation hypothesis. So let's actually get into the physics, right? All right, so they have some methods. Oh, they're going to use some very powerful stuff. In order to assess which resources are needed to simulate a given system, we need to quantify how much information can be encoded in a given portion of the universe, or in its totality. The holographic principle arguably represents the most powerful tool to establish this connection. The holographic principle is this notion in physics, which is kind of like it's like a unifying principle that seems to be super relevant for our universe, which relates information in the interior of something to information on the surface of something. In particular, it gives us a constraint onto how much into how much information there could be in a given region of spacetime. For those who are just joining us, this paper is going to debunk the simulation hypothesis, at least several versions of it. So stick around, it should be interesting. The holographic principle arguably represents the most powerful tool to establish this connection. It was inspired by the modeling of black hole thermodynamics through the Bekenstein bound, see below, according to which the maximum entropy of a system scales within its encompassing surface rather than its enclosed volume. That's what I was just saying. So the entropy of a system roughly captures how much information is stored in that system, and it turns out that the information stored in a black hole depends on its surface area rather than its volume. That was kind of like the first inkling of the holographic principle. The holographic principle at its core is at the core of the powerful ADS-CFT correspondence, where ADS stands for anti-de Sitter spaces and CFT for conformal field theories, which links string theory with gravity in 5 dimensions, with the quantum field theory of particles with no gravity in 4-dimensional space. This was a very famous paper in 1998. This is what made Juan Maldacena famous. He was the author of the ADS-CFT correspondence. It's a string theory thing, but it's kind of been broadened since then. According to the holographic principle, a stable and asymptotically flat spacetime region with boundary of area A is fully describable by no more than A divided by 4 degrees of freedom, or about 1 bit of information per Planck area defined as this. So this is the crux. If you have if the holographic principle is true, which we have good reason to think that it is, then that means that the amount of information that it takes to describe a region of spacetime is directly proportional to the surface area of that region. And in particular, it's exactly 1 bit of information for every 4 Planck areas. And so a Planck area is roughly 10 to the minus 66 square centimeters. Very, very small. LP here is the Planck length. You may have heard of that before. So here, that's 10 to the minus 33 centimeters is the Planck scale. So, while in a local classical field theory description, there are far more degrees of freedom, the excitation of more than A over 4 of these degrees of freedom will trigger gravitational collapse. What this is saying is that, if you were to try to pack more information into a space that has that surface area, that information would require enough energy that it would collapse into a black hole. And so you wouldn't have access to all of that information anymore. The total entropy contained within a holographic area A follows from the generalized second law of thermodynamics, giving the Bekenstein bound, which applies to systems which are not strongly self-gravitating, and whose energy is E equals mc squared. So here we have the entropy of some region with area A, so the entropy must be less than the area divided by 4, and the entropy is related to the energy of the system by E equals mc squared, and the mass and the radius of the sphere that fits around it, and a few other constants. Kb is the Boltzmann constant, h bar is Planck's constant, c is the speed of light, all these lovely things. So here it says that r is the circumferential radius of the smallest sphere that fits around the matter system, assuming nearly Euclidean spacetime for simplicity, and m is the mass of the system. So, so the Bekenstein bound gives us a relationship about the mass. The Bekenstein bound tells us the maximum amount of energy that can be contained, entropy, which can be contained in a volume with a certain surface area. This is an upper bound on the amount of entropy, yes. And it's bounded above by essentially the size of a Schwarzschild. It's bounded above, this depends on the amount of mass that you can cram into a certain volume, which is bounded above by this, basically the amount of mass that you could fit into there without forming a black hole. Because if you form a black hole, well, then it'll just grow as you add more and more mass. Yeah, let's read this footnote. As a sign of respect for what this astrophysicist honestly thinks is the only real universe, which is the one we observe through telescopes, I will still use the capital letter for this universe, even if for the sake of argument, this is at times assumed to just be a simulation being run in another universe. That's kind of funny. Right, okay, so we have a bound on the amount of entropy, which is a measure of information, and it relates to the energy of the system. So that's an important thing, because, we're going to talk about the amount of energy that it takes to simulate a universe, and so they're going to calculate the entropy of the universe, presumably, and they're going to say, well, it takes more energy than that, something like that. Okay, so now we're going to proceed by relating the entropy and the energy, presumably, to even more informational things. Next, we can use the classical information energy equivalence. This is from Leo Szilard from 1929, which states that the minimum entropy production connected with any 1-bit measurement is given by h equals Boltzmann's constant times log base 2. So this is asking, how does the entropy relate to some measurement of a bit, like a bit in like a computer. So log 2 reflects the binary decision, of course. The amount of entropy for a single 1-bit measurement, or for any single 1-bit flip, i.e. a computing operation, can be greater than this fundamental amount, but not smaller, otherwise the second law of thermodynamics would be violated. So you can never produce less entropy by flipping a bit than the Boltzmann's constant times log base 2. Therefore, the total information in bits that can possibly be encoded within the holographic surface is this much. So we just divide the entropy, or we divide the upper bound of the entropy anyway, by this minimum entropy production for a 1-bit measurement, and this will give you the maximum amount of information that you could. What was it trying to say? This is the maximum amount of bits that you could. Sorry, the minimum amount of bits that you could flip that would produce that much entropy, and it's just s divided by h, so it's this number divided by kb log base 2. So we get a thing that depends on the energy. Name of the paper. For those who are just joining us, the paper is Astrophysical Constraints on the Simulation Hypothesis for this Universe, why it is nearly impossible that we live in a simulation. Right, so continuing, so this basically, so the amount of, so if the energy in a space-time volume is bigger, then you could encode more information in that. Essentially that, sorry, I want to make sure I get this right. You could have more flips and still produce that amount of entropy. Similarly, if the radius of your space-time volume gets bigger, then you could again encode more flips. So now we get to the question of physical devices, right? how much energy is required to encode an arbitrary amount of information, I, in any physical device? Computation and thermodynamics are closely related. In any irreversible computational, let's check out what they mean by irreversible. It must be noted also that reversible computation with no deletion of bits or dissipation of energy is possible. However, irreversible computation is unavoidable both for several many-to-one logical operations and or erase, as well as for error correction, which several erroneous states are mapped into a single correct state. So they're going to use irreversible computation. So in any irreversible computation, information must be erased, which is a physical reduction of the number of possible states of one physical register to 0. This necessarily leads to the decrease of entropy of the device used for computing, which must be balanced with an equal or larger increase in entropy of the universe. Thermodynamics thus leads to the necessity of dissipating energy via heat to erase bits of information. So if you want to erase a bit, that would reduce the entropy of the system. So that entropy must increase somewhere else, and the only way to do that is to release energy. The related cost of erasing one single bit is thus given by Brioun's inequality. So the amount of energy that you must emit to erase a single bit of information is Boltzmann's constant times the outside temperature times the log base 2. T is the absolute temperature where the energy gets dissipated. It's where you're dissipating the energy to. So if it's hotter outside, it takes more energy to dissipate to the environment, or you have to dissipate more energy to the environment, which arguably explains why computers run less efficiently when it's hot, because they don't have to use as much. They have to use more energy. If we apply this to the maximum information within the holographic sphere, which is what we're talking about here, we get that E1. This is the amount of energy that must be dissipated in order to flip that number of bits that encodes the information that account for all of the data, or that account for all of the properties within a space-time volume of a certain size, is this much. So it's the temperature times Boltzmann's constant times the energy times the radius divided by some constants. So it's interesting to compute the ratio between the enclosed energy within the holographic surface E and the energy required to encode the same information. So there's actually like energy within a space-time volume, right? Like there's matter and stuff happening. And then there's the question of how much energy does it take to encode that much, the information that describes that system. And so that ratio, I guess, is interesting. And it turns out that ratio is about 27.5 times the temperature divided by 1 Kelvin times the energy divided by 1 erg, or put another way, it's 0.04 times the temperature divided by 1 Kelvin times the mass divided by the Planck mass. So this is to say that, if you know the mass in the interior, then you know how much so for example, let's say that the temperature was 25. That would make the 25 Kelvin. That would make this 0.04 out front just equal to 1. And so that would mean that the amount of energy it takes to encode 1 Planck's mass worth of matter in a particular space-time volume would be equal to the amount of energy in that space-time volume, right? So this is just a relationship between how much energy it takes to encode the information versus how much energy you're trying to describe. This physically means even at the low temperatures of 1 Kelvin for computing, the minimum energy required to fully describe all internal degrees of freedom becomes larger than the actual energy that the system contains already for a system with mass of about 25 Planck constants or more. That's what I was just saying, actually. This is enlightening as it shows how the full simulation of any macroscopic or astronomical object is bound to require an astoundingly large amount of energy, which in turn allows us to assess the plausibility of the simulation hypothesis against known astrophysical bounds. So that's what they're trying to get at. In order to simulate a system, simulating a system requires wildly more energy than the system itself contains. So they're going to use that to try to say that the simulation hypothesis is nonsense. So the exact bounds derived from equation 4 depend on what systems are considered and how R, E, and S are defined. Equation 4 was this equation, by the way. This is the maximum information, the total information that can be encoded within that area. It must also be stressed that a key assumption in Bekenstein's derivation formula is that the gravitational self-interaction of the system can be neglected, as it is highlighted by the fact that the Newton constant g does not appear. Although in the application explored in this work, this assumption is reasonably verified, we notice that the estimates for black holes can significantly differ. So fine. Yeah, so the point is it's not that it's exponentially greater than the simulated E, but it is greater. And there's a lot of energy in a small amount of mass. All right, let's talk about the results. They're actually going to tell us, they're actually going to go through and, you know. Okay, so they're going to first talk about what would be required if the full universe was simulated, right? Based on the above formulas, we can first estimate the total information contained within the holographic surfaces with radius equal to the observable radius of the universe, which is 14.3 gigaparsecs co-moving. That amounts to about 96 or 94 billion light years across. And we're going to assume that we know the density of the universe, which we do. This is something that we can measure. It is about 8.5 times 10 to the minus 30 grams per cubic centimeter, which is valid for a flat universe now. Z equals 0 is now. And using a value for the Hubble constant of 67.4 kilometers per second per megaparsec. Again, the Hubble constant is a thing that we can measure. It's roughly the rate of expansion of the universe. Although I don't know why that's showing up. Oh, you need the Hubble constant and the critical density in order to find the total mass, or the total energy. So that's fine. So the total energy in the universe is roughly, so it's the radius of the universe times the density. Oh, I guess they don't need the Hubble constant. Why do they need the Hubble constant? And times the speed of light squared. So the total energy of the universe is approximately 10 to the 78 ergs. Now, if you don't know what an erg is is 1/10,000,000th of a joule. So this is 10 to the 71 joules. It's a lot. It's a lot of joules. Lots of energy in the universe. Based on equation 4, this results into a maximum information of bits of, well, if you just plug it into equation 4, which is up here, this is the maximum amount of the total information that can be encoded in our universe, is 10 to the 124 bits. Keep in mind, there's about 10 to the 80 atoms in the universe. So this is 44 orders of magnitude more than the number of atoms in the universe. That's how many bits are encoded in the universe. And so this would require 10 to the 100 or almost 10 to the 109 ergs of encoding energy. Assuming a computing temperature equal to the microwave background temperature, or the microwave background temperature nowadays, which is 2.7 Kelvin. So if you're doing a computation even in the vacuum of space where it's super, super cold, you would require 10 to the 109 or 10 to the 102 joules of energy to simulate the observable universe. As anticipated, since EIU, this is the energy required to encode the universe, is significantly greater. It's 30 orders of magnitude greater, by the way. So we have 30 orders of magnitude between these two. Is significantly greater than the energy of the universe. There simply is not enough energy within the entire observable universe to simulate another similar universe down to the Planck scale, in the sense that there are not even remotely available resources to store the data and even begin the simulation. Therefore, the simulation hypothesis applied to the entire universe is entirely rejected based on the energy beyond imagination it requires. As noted, slightly different estimates for the total information content of the universe can be obtained replacing the Bekenstein bound with the Hawking-Bekenstein formula, which computes the entropy of the universe if that would be converted into a black hole. So it could be that the information could be different by like less than an order of magnitude. The maximum information stored would be 2 times 10 to the 124 bits rather than 3.5 times 10 to the 124 bits, which is in line with similar estimates in the recent literature. Once we rescaled the previous formula for the volume within the cosmic event horizon rather than the volume within the observable universe, blah, 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 blah. And obviously, incredibly larger than the amount of information which is generated even by the most challenging cosmological simulations produced to date in astrophysics. So in astrophysics, they do a lot of simulations, and they might produce, 10 terabytes of data, maybe, of raw data. So this is weird that they bold it like this, but this leads to the first conclusion. Simulating the entirety of our visible universe at full resolution, i.e. down to the Planck scale, is physically impossible. Great. All right. So what if it's not the whole universe that's being simulated? What if it's just the Earth? Next, we can apply the same logic to compute the total memory information needed to describe our planet. So we know the size of the planet, we know the mass of the planet, we know the energy stored with the total energy of the planet. We assume here that a planet is the smallest system that the simulator must model to recreate the daily experience that humankind collectively considers the reality. Let's read the footnote. For the sake of argument, since we surmise here the existence of a skilled simulator, which somehow can use computing centers as large as a planet-sized black hole, we can concede with no difficulty that it can also create a consistent simulation of the experience of 10 to the minus 3 astronauts that have temporarily left our planet and have probed a larger portion of space. The simulator must also use a modest amount of extra computing resource to produce fake data to constantly keep astrophysicists and cosmologists busy while they think they study the universe. So again, we're going to use equation 4 to estimate the information that is contained in a full quantum description of our planet. It's 10 to the 74 bits of information, or 10 to the 75 or so. And for the total energy needed to encode this information, you need 10 to the 59 ergs of energy. Significantly less than the whole universe, but still a lot. Assuming very optimistically, as it will be discussed later, that the temperature is the temperature of the CMB. The amount of energy required to even start the simulation of our planet is enormous. That would be this amount of energy, and it can easily be put into astrophysical context. So this is the same order of rest mass energy of globular clusters. So these are like clusters of stars that have like 10,000 stars in them. This is also the order of the potential binding energy of the halo of our galaxy. So it's like the gravitational potential energy of our entire galaxy. Therefore, the initialization of a complete simulation of just a planet like Earth requires either to convert into energy the entire stellar mass of a typical globular cluster, or to use the equivalent energy necessary to unbind all the stars and matter components in the Milky Way. Elaborating on the implausibility of such a simulation based on its energy cost is straightforward. While this is indeed the requirement just to begin the simulation, roughly the same amount of energy needs to be dissipated for each time step of the simulation. This means that already, after 10 to the 6 time steps, the required energy is equivalent to the entire rest mass energy of the Milky Way, or roughly to the total potential energy of the most massive clusters of galaxies in the universe. So, every single time step, you have to basically blow up a galaxy. Yeah, Jake, that's exactly what's happening. You have to blow up a galaxy for every time step that you want to simulate Earth. Moreover, while the minimum mass required to contain this information corresponds to a black hole mass prescribed by equation 11, which gives 0.32 times the mass of the sun, the actual energy required to encode the entire amounts of bits can at most be confined within a radius corresponding to the Schwarzschild radius of 5 billion centimeters. So that is the energy required. So what they're saying is, you're going to use a certain amount of energy to encode this number of bits, right? Now, if you put all this energy in into a small area, it'll form a black hole. So your computer has to be at least as big as the black hole that the energy would fit into. And so this is saying that you would need a black hole that's at least 5 billion centimeters across. Your computer would have to be at least 5 billion centimeters across, otherwise it would collapse into a black hole. Yeah, notably, this is 70% the radius of Jupiter, meaning that planetary-sized computer must be deployed for the simulation. The equivalent mass enclosed within such a radius will, of course, be very large. It is roughly the mass of 10,000 suns. Moreover, 100,000 suns. Moreover, such computing Jupiter, that's funny. Such computing Jupiter must be continuously supplied with a similar amount of energy for each time step, while all dissipated energy is somehow released outside of the system, and even without raising the computing temperature, which makes this scenario even more implausible. So you have to have a Jupiter-sized black hole, not like a Jupiter mass black hole, a Jupiter-sized black hole, which has the mass of 10,000 suns, and you have to feed it 10,000 suns worth of energy every time step, and you have to somehow dump 10,000 suns worth of energy every time step to just simulate the Earth. Interestingly, such planetary-sized computers were theoretically explored by Sandberg, who presented a thorough study of all practical limitations connected to heat dissipation, computing power, connectivity, and bandwidth, arriving to a typical estimate of 10 to the 47 bits for a realistic Jupiter-sized computer. So if you wanted to build a Jupiter-sized computer, you could get a 10 to the 47-bit computer. Keep in mind, we needed 10 to the 74 bits to simulate the Earth. So It is 27 orders of magnitude fewer than what is required to encode the maximum information within the holographic surface content of our planet. Even setting aside the tremendous distance between hypothetical and realistic memory capacity of such colossal computers, the next problem is that concentrating so much mass and energy in such a limited volume will inevitably produce levels of high energy emission and heating, as in standard black holes and their related accretion disks. If a black hole actively accretes matter, the kinetic temperatures acquired by accreted matter is very large. So as you're dumping stuff into your black hole sized computer, that stuff gets very, very hot because the black hole computer has enormous gravity, and so things will fall in very quickly and heat up very significantly. And so the temperature of the stuff falling in will get very, very hot. It'll get to this temperature in particular, which is a lot. I.e., regardless of the actual mass and radius of the black hole in consideration, the temperature acquired by accreted particles is about the mass divided by the Planck mass, where the Planck mass is just the mass of a particle, times 10 million Kelvin. Sorry, this is not the Planck mass, this is the proton mass. Such temperature is manifestly much larger than the very optimistic CMB temperature we previously assumed to compute the minimum energy necessary to encode the full information of the simulation. I.e., when you're dumping stuff into your black hole computer, the outside temperature is about 10 million times hotter than the CMB is, which means that it will take 10 million times more energy. It follows that the actual energy requirement is 10 to the 7 times larger, even in the most optimistic configuration, requiring now a computer with radius of 0.16 parsecs, or about half a light year. So now your black hole supercomputer, which is simulating just the Earth, has to be a black hole that's half a light year across. It's just the Earth. This leads to the second conclusion. Simulating planet Earth at the full resolution, i.e. down to the Planck scale, is practically impossible as it requires access to a galactic amount of energy. Literally galactic. You'd have to blow up a galaxy every single time step. You'd have to blow up 10 million galaxies every single time step. Which is absurd. This isn't a classical or quantum thing. This is just information. This is just like theoretical computer science analysis. It has nothing to do with quantum computers or classical computers at all. Like, this is just the amount of energy that it takes to do bit flips. Next, we shall explore the possibility of partial or low-resolution simulations of planet Earth, in which the simulation must only resolve scales which are routinely probed by human experiments or observations, while using some sort of subgrid physics for any smaller scale. The Planck scale, LP, is at the core of physics as we know it, but it is not a directly measurable scale by any means. In the framework of the simulation hypothesis, it is well conceivable that the Planck length appears in the equations of our physics, but that the simulation instead effectively works by discretizing our reality at a much coarser scale, thus providing a low-resolution simulation. So the idea is that, look, we don't need to simulate. Maybe we don't need to simulate all the way down to the Planck length. We can just simulate to some smaller thing that we can just simulate to whatever level is necessary that humans have access to. So what is the smallest scale, delta x min, that a realistic simulation of our planet should resolve in order for the simulation not to be incompatible with available human experiments or observations done on the planet? Well, high energy physics through the de Broglie relation, lambda equals hc over E, which is h over p. P is the momentum. So lambda is the wavelength of some quantum state, and p is the momentum, establishes an effective link between observed energy particle phenomena and spatial length scales. So the smallest resolution that the simulation must have depends on the highest energies which are routinely probed by human experiments. On Earth, the smallest high-energy scale probed by man-made experiments is in the 10 to the minus 16 centimeter ballpark, based on the particle collision energy reached by the Large Hadron Collider. However, this is true only limited to the portion of the terrestrial surface where the LHC is deployed. So, they only need to have high-level simulations where the LHC is. They can have low-level simulations everywhere else. Fairly small. A much larger energy scale is probed by the detection of ultra-high energy cosmic rays as they cross our atmosphere and trigger the formation of observable Cherenkov radiation and fluorescent light. Observed ultra-high energy cosmic rays are characterized, so cosmic rays are particles from space, by the way, and we just see them all the time because we get, like, we get flashes of light in the sky, basically. Observed ultra-high energy cosmic rays are characterized by a power law distribution of events, and the largest energy ever recorded is 3 to the 20th electron volts. This was the oh my god particle. I made a video about it a while ago. While the second probably exceeded the 10 to the 20 EV range, this was the Amaterasu particle, which I also made a video about. The precise determination of very energetic is subject to absolute energy calibration uncertainties, of course. Also due to their uncertain composition, hence we can use the energy of 10 to the 8th ergs as a conservative limit. This yields a length scale of 10 to the minus 24 centimeters. However, a hardcore proponent of the simulation hypothesis might still argue that this spatial scale is not really the most stringent experimental limit on the minimum spatial scale of the global Earth simulation, because ultra-energy cosmic rays probe only the last, say, 100 kilometers of air above the ground level, where the particle cascades and air showers are triggered by the interaction between the ultra-high-energy cosmic rays and air molecules. Hence, the majority of the simulated volume of our planet might still be kept at a much lower level of spatial resolution by the simulator in order to limit computing resources. And indeed, the best resolution, which is currently sampled for the interior of Earth, based on the advanced analysis of seismic shear waves diffracting along the core mantle boundary, is just of order 100 kilometers. So, below the surface of the Earth, they can have really low resolution, right? Luckily, high-energy astrophysics still comes to the rescue due to the detection of very high-energy extragalactic neutrinos crossing the inside of our planet. Since the first discovery of energetic neutrinos by the IceCube Observatory, so by the way, when they say save the day, what they're going to get at is that we actually get better resolution than 100 kilometers, because we have neutrinos that pass through the entire Earth. Since the first discovery of energetic neutrinos by the IceCube Observatory, the existence of a background radiation of neutrinos, likely of extragalactic origin, in the 10 TeV to 2 PeV energy range has been firmly established. There are high-energy neutrinos. Yeah, true. Since such neutrinos are very likely produced in external galaxies, even if the exact mechanism is highly uncertain. Yeah, we actually don't really understand how these high-energy neutrinos are made yet, by the way. I'm going to sip me some water. If you guys like what you're doing, by the way, consider supporting me. You can support on YouTube, on YouTube, on Cash App, on TikTok. Buy me a coffee, all these great things. In any case, the maximum energy scale probed so far reaches about 10 to the 17th EV, i.e. lower than the maximum energy reached by UHECRs, but in line with theoretical expectations about the likely hadronic production mechanisms at the source. Unlike UHECRs, however, neutrinos cross our planet entirely, since they are extremely weakly interacting with anything else. As a matter of fact, the IceCube Observatory is more sensitive to events which are produced on the other side of the planet. By the way, this is a debunk of flat Earth, because neutrinos literally come up from the other side of the planet. With respect to its location on the South Pole, as this reduces the contamination by lower energy neutrinos of atmospheric or solar origin. Therefore, the established detection of this event can be used to constrain the minimum length scale which must be effectively adopted by any low-resolution simulation of our planet at 10 to the minus 21 centimeters, which is very small. Let's read the footnote. Especially because we focus here on the simulation of the Earth, a reasonable question would be whether such low-resolution simulation would still be capable of reproducing the observed biological process on the planet. A 10 to the minus 21 centimeter length seems to be safely smaller than any process known to be relevant for biology, and thus a hypothetical simulation using an efficient subgrid modeling of processes below such resolution might correctly reproduce biology on Earth. If instead some biological processes will be shown to depend on less than 10 to the minus 21 centimeter scales, this can be used to revise our constraints on the small scale to be resolved by the simulation and call for an even more implausibly large amount of energy or power. So this is the scale that they're going to use for the entirety of the center of the Earth. A simulation with an effective resolution coarser than this will be incompatible with our experimental data on neutrinos. Less straightforward is how to use this knowledge to estimate the information required for such reduced resolution simulation of planet Earth using the holographic principle as before. The most conservative choice appears to still be to apply the holographic approach, but rescaling the application of equation 4 to the minimum element of area possible in the low resolution simulation, instead of using the Planck area. So they would use the neutrino length rather than the Planck length. Therefore, the minimum necessary information to be encoded follows from rescaling equation 12 for the ratio of the two areas. So this says that we would need 1.65 times 10 to the 51 bits for this low resolution version of the Earth. This gives a minimum encoding energy of 4 times 10 to the 35 ergs if we use conservatively that the temperature is the cosmic microwave background radiation, which we are going to relax later on. At the face value, this energy requirement is far less astronomical than the previous one. It corresponds to the conversion into energy of, say, 10 to the minus 19 suns. Not that much. This is still equal to the total energy radiated by the sun in 2 minutes, considering the solar constant, yet it is an amount of energy which is which a fairly advanced civilization might possibly have access to. Equation 11 gives the size of the minimum black hole for storing this amount of information, which is very, very small. The radius relative to this mass is also fairly small, 10 to the minus 7 centimeters. Therefore, while the total energy required for the initial encoding of the simulation's data is still immense by modern human standards, it is tiny in astrophysical terms. However, next we are going to show that the only way to process the data of such simulation to advance it at a large enough speed is the access to unattainably large computing power, which makes this last low-resolution scenario impossible as well. For those who are just joining us, the paper we're reading is Astrophysical Constraints on the Simulation Hypothesis for this Universe, Why It is Nearly Impossible That We Live in a Simulation. Where were we? Around here? Yeah. We largely refer to here the seminal work of Lloyd for the computing capabilities of black holes. The ultimate compression limit of a black hole can provide, in principle, the most performing computing configuration for any simulation. Thus, by showing that not even in this case the simulation can be performed, we can argue about its physical impossibility. Based on the classical picture of black holes, no information is allowed to escape from within the event horizon. However, the quantum mechanical view is different, as it allows, through the emission of Hawking radiation, as black holes evaporate, to transfer some information on the outside. Following Lloyd, even black holes may theoretically be programmed to encode the information to be processed within their horizon. Then an external observer, by examining the correlations in the Hawking radiation emitted as they evaporate, might be able to retrieve the result of the simulation outside. So they're literally saying, what if you actually used a black hole as a computer? Because you can, like Lloyd showed, that you can actually make computations using black holes. Even such a tiny black hole has a very long evaporation timescale. With it's this. This is the formula for it. With the constant k being 10 to the minus 3 to 10 to the minus 2, depending on the species of particles composing the bulk of the black hole mass, which gives an evaporation time of 10 to the 35 seconds. The temperature relative to the Hawking radiation for such a black hole is given by this. So it's about 100,000 Kelvin. Quantum mechanics constrains the maximum rate at which a system can move from one distinguishable quantum state to another. So they're going to try to talk about how quickly this quantum black hole can do computations. A quantum state with an average energy E bar needs a time of order at least delta t, this is related to the uncertainty principle, to evolve into another orthogonal and distinguishable state, and hence the number of logical operations per unit time, i.e. the computing frequency, that can be performed by a computing device is the inverse of the timescale from the Heisenberg uncertainty principle. So roughly the frequency, the computing frequency, is proportional to the average energy of the quantum state. If such a black hole calculator uses all its storage memory, its maximum computing power per bit, i.e. the number of logical operations for each single bit, is estimated to be this. So this is the number of operations that it can perform for number of logical operations that it can perform per bit is this much, where S is the black hole entropy. The link between the thermodynamic entropy and temperature here is given by, so it's the temperature is the rate of change of the entropy with respect to the energy. So let's think about this for a minute. If it uses all of its storage memory, what does that mean? So I don't see how the frequency is involved here. Why is the frequency involved? Because the frequency is why this term is showing up. Okay, so let's think about this. So did they just divide the frequency by the? Did they just divide the frequency by the number of bits? Yeah, I guess they just divided the frequency by the number of bits, which is kind of strange. It's the number of logical operations for each single bit. I guess number of logical operations per second for each single bit, right? Right, anyway. By integrating the relationship linking Ts and E, we get that T is a constant times the energy divided by the entropy, in which C is a constant of order unity, which depends on the actual medium being used. That's not really super relevant. This is the computational frequency. This is the rate at which the black hole computer can actually do computations. The dependence between the computing power and the working temperature is manifest. The entropy governs the amount of information the system can register, and the temperature governs the number of operations per bit per second it can perform, as beautifully put by Lloyd. So, yeah, okay, so entropy tells you, how much, how many bits you can store, and the temperature tells you, because the temperature is related to energy here, the temperature tells you how many operations per bit per second you can do. Okay, cool. Estimating the working temperature of such a device is not obvious. As an upper bound, we can use the temperature of accreted material at the event horizon. So we need to know, so computers dump energy out to the external world, and that's the working temperature. So they need to know how hot the outside of the black hole is. As an upper bound, we can use the temperature of accreted material at the event horizon of an astrophysical black hole, which is about 10 million Kelvin. And so they get that the operations per bit per second are about 10 to the 17th. This is for like a normal stellar-sized black hole. It's about 10 to the 17th operations per bit per second. It's a very fast computer. By multiplying the total number of bits encoded in such a black hole, we get its total maximum computing power. So you just multiply the bits by the number of operations per bit per second, and you get that a stellar mass black hole computer could perform 10 to the 60, or almost 10 to the 69 bit flips per second, which is like a lot. On the other hand, if the black hole does not accrete matter, the lowest temperature at the event horizon is the temperature relative to the Hawking radiation, which in this case would be 10 to the 5th Kelvin for the mass that was under consideration up here. Oh no, I'm sorry. This is the operations per second for this small black hole. The black hole that's like, 1/10 millionth of a centimeter. So you have to take it. So the temperature of the Hawking radiation is 100,000 Kelvin. So you get slightly fewer. Yeah, you get slightly fewer operations per bit per second. And so you get slightly less computing power because it's not as hot outside. It's not clear to me why the temperature outside should be related to the rate at which you can do computations. You'd think it would be the opposite, but I guess I would have to go read the Lloyd paper. Anyway, I guess we get that relationship here, that it's proportional to the temperature, it's proportional to the energy, which is proportional to the temperature. So maybe it checks out. All right, let's keep reading. This computing power may seem immense, yet it is not enough to advance the low-resolution simulation of planet Earth in a reasonable wall clock time. We notice that the minimum time step that the simulation must resolve in order to consistently propagate the highest energy neutrinos we observe is 10 to the minus 32 seconds. In the extremely conservative hypothesis that only a few operations per bit are necessary to advance every bit of the simulation forward in time for a delta time step of delta t time step on the order of for a delta t time step, you need 10 to the 31 operations on every bit. Wait, hold on. What is the sentence saying? Yeah, an order of 10 to the 31 operations on every bit are necessary for the simulation to cover just 1 second of evolution of our universe. That's so many. The two previous cases instead can at best achieve 10 to the 15th or 10 to the 17th operations per bit per second, which is 10 to the 15th and 10 to the 17th, depending on the working temperature. In that condition, a single second in the low resolution simulation, so this is how many operations must be performed on every bit every second in order to get, or on every bit in order to advance the time step of our universe forward by 1 second if our universe is, or if our Earth is a low resolution simulation. But the black hole that can encode all of that information can only do 10 to the 15th to 10 to the 17th operations per bit per second. And so that would mean that in those conditions, a single second in the low resolution simulation of planet Earth requires 10 to the 13th seconds of computing time, or 10 million years to advance the clock forward by 1 second on Earth on the lower end, and 100 million years at the upper end. It's so much. Which are in both cases absurdly long wall clock times. Therefore, an additional speedup of order 10 to the 15th to 10 to the 17th or larger would be necessary in order to advance the low resolution simulation of Earth faster than real time. So you would need to make a computer a quadrillion times faster than the fastest possible computer, namely a black hole. So 1 trillion times faster than the fastest possible black hole in order to match the clock on Earth with the clock in the simulation. In this case, the necessary computing power will be just impossible to collect. You would need to dump 10 to the 73 ergs per second into this computer, which again, as a reminder, let's go look for comparison. That is 14 orders of magnitude. That would be blowing up the equivalent of a quadrillion galaxies every second to get that speed up. Which means to convert into energy many more than all stars in all galaxies within the visible universe. So you'd have to take an entire visible universe's worth of stars, turn them entirely to energy, and use that, and that would simulate 1 second of Earth, of low-resolution Earth. No known process can even remotely approach this power, and thus also this scenario appears absurd. This leads us to the third conclusion. Even the lowest possible resolution simulation of Earth, at a scale compatible with experimental data, requires geologically long timescales, making it entirely implausible for any purpose. 1 second is 10 million years. Okay, there's more to say though, because as a lot of you have said, oh, but what if it's outside the whatever? Needless to say, in such a murky physical investigation, several assumptions can be questioned, and a few alternative models can be explored. Here we review a few ones which appear to be relevant, even if it's anticipated that the enthusiasts of this simulation hypothesis will probably find other ways out. A reasonable okay, so section 4, can highly parallel computing make the simulation of the low-resolution Earth possible? A reasonable question would be whether performing highly parallel computing could significantly reduce the computing timescale at the end of section 3.3. In general, if the computation to perform is serial, the energy can be concentrated in particular parts of the computation, while if it's parallelizable, the energy can be spread out evenly among the different parts of the computer. My guess is the answer is no, but let's keep reading. The communication time across a black hole horizon is of the same order of time to flip a single bit. Hence, in principle, highly parallel computing can be used here. However, the somewhat counterintuitive result is that the energy E is divided among n processors and processing units, each operating at a rate of, this processing rate of energy divided by the number of processors. The total number of operations per second performed by the black hole remains the same. This strictly follows from the quantum relation between computing time and spread in energy explored in section 3.3. Thus, if the energy is allocated to more parallel processors, the energy spread on which they operate gets smaller, and hence they run in proportionally slower way. So basically, you want to have more energy concentration so that they can run faster. More energy concentration in a black hole means it runs faster. Finally, if the computing is spread to a configuration significantly less dense than a black hole but keeping the same mass, the higher levels of parallelization can be used, but the computing time will increase as a black hole computer already provides the highest number of operations per bits per second. So parallelization doesn't save you. Okay, what if time stepping is not the one given by neutrino observations? Okay, maybe we don't need to time step maybe we don't need 10 to the minus 31 seconds as a time step. What if, for reasons beyond what our physics can explain, high-energy neutrinos can be accurately propagated in the simulation with a time stepping much coarser than 10 to the minus 32 seconds? In this case, the next constraint to fulfill is still very small, and given by the smallest time interval that humans could directly measure so far in the laboratory, which is 10 to the minus 20 seconds. In this case, applying the same logic, we get that the CPU time is 10 to the 4, is 1,000 seconds depending on the computing temperature, which still means a simulation running several orders of magnitude slower than real time. So you would need 1,000 seconds on the wall in order to simulate 1 second of low-resolution Earth. Moreover, even in this scenario, the amount of power to process is literally out of this world, 10 to the 47 ergs per second, if we rescale appropriately. This power is astronomically large, but not entirely impossible. Mergers between massive clusters of galaxies, which are among the most energetic exchanges of matter in the universe, only produce 10 to the 45 ergs per second of power. Distant quasars can radiate up to 10 to the 47 ergs per second of power, while supernova can release up to 10 to the 52 ergs per second of power, mostly in the form of energetic neutrinos, and only in the first 1 to 10 seconds of their explosion. Gamma ray bursts from hypernova can dissipate up to 10 to the 54 ergs per second on timescales of days. Finally, the detection of gravitational waves by merging black holes probed energy dissipation rates of several 10 to the 56 ergs per second, but limited to a short timescale of the coalescence. In any case, conveying in a steady way such gigantic amounts of energy through the microscopic black hole required for this very low resolution scenario appears as an impossible task. So keep in mind, you'd have to focus basically the energy of a supernova every second into a black hole that's a 10 millionth of a centimeter across. You'd have to focus all of that energy into a place like the size of, a cell. Seems kind of impossible. Okay, what about quantum computing? By exploiting the fundamental quantum properties of superposition and entanglement, quantum computers are more performing than classical computers for a large variety of mathematical operations. Grimlock, thank you for the $10. I appreciate you. In principle, quantum algorithms are more efficient in using memory, and they may reduce time and energy requirements by implementing exponentially fewer steps compared to classical programs. However, these important advantages compared to classical computers do not change the problems connected with this simulation hypothesis analyzed in this work, which solely arise from the relation between spacetime information density and energy. According to the holographic principle, the information bound used here is the maximum allowed within a given holographic surface with radius r, regardless of the actual technique used to reach this concentration of information or to process it. Moreover, our estimated computing power does not stem from the extrapolation of current technological performances of classical computing, but it already represents the maximum possible performance obtained in the futuristic scenario in which a black hole can be used as an ultimate computing device. In summary, while quantum computing might in principle be the actual way to get the maximum computing speed physically allowed at the scale of black holes, or in any other less extreme computing devices, this technology will not be able to beat the currently understood limits posed by physics. Yeah, so like somebody was mentioning earlier, they were like, but they're not going to use classical computers, they're going to use quantum computers. No, this is a fundamental problem of computation, period. We're not talking about any particular model of classical computing here. We're not talking about like literal physical bits flips in your computer. We're talking about like the information that describes quantum states themselves, right? So like, quantum computing doesn't save you here, obviously. Okay, all right, so there's still quite a bit more. What if the holographic principle doesn't apply? Okay, fine. So maybe it doesn't. One possibility is that the holographic principle, for whatever reason, does not apply as a reliable proxy for the information content of a given physical system. I mean, maybe the holographic principle is wrong, but It's worth reminding that the holographic principle prescribes the maximum information content to scale with the surface and not the volume of a system. Hence, it generally already provides a very low information budget estimate compared to all other proxies in which information scales with the volume instead. In this sense, the estimates used in this paper, including in the low-resolution simulation of Earth in section 3.3, already appears as conservatively low quantities. Why do we have a Nazi in chat? All right, he's gone. If the holographic principle is not valid, then a larger amount of bits can be encoded within a given surface with radius r, in contradiction with our understanding of black hole physics. This will allow the usage of smaller computing devices, but at the same time, it will require even more computing power, making the simulation hypothesis even more implausible. On the other hand, while the holographic principle prescribes the maximum information which can be encoded within a portion of spacetime, the actual evolution of the enclosed system might be described with fewer bits of information. Maybe. The holographic principle is much broader than just ADS. It's just ADS is the most, the emblematic example of the holographic principle. For example, in recent work with Vazza, we used mathematical tools from information theory to show that on macroscopic scales, the statistical evolution of the cosmic web within the observable universe can be encoded by using only 10 to the 16th bits of information. This is, of course, incredibly less than 10 to the 124 bits estimated in section 3.1 and following from the holographic principle. However, the latter includes all possible evolution on all scales down to the Planck length, in which a plethora of multiscale phenomena obviously happens. While the concept of emergence and efficiency of prediction for complex multiscale phenomena is powerful and useful tools to compress the information needed to describe physical patterns forming at specific scales, a full errorless simulation of the multiscale system seems to require a much larger amount of information. Basically, they're just saying you can't really do much compression, right, on like the information in our universe because there's a lot of multiscale stuff happening. Like there's a lot of interactions between like atomic stuff to cell size stuff and cell size stuff to macroscopic stuff to planet size stuff. There's a lot of like cross scale interactions. So they're saying that you can't do a whole lot of compression. In essence, we shall conclude that while it is well conceivable that the actual information needed to fully capture the evolution of multiscale phenomena emerging on different scales can be further reduced, it's implausible that the information budget quoted in this work can be reduced by several orders of magnetism. So even if the holographic principle is wrong, it's still implausible. Okay, plot twist. This is the part that you guys have been waiting for. Inner Sean Connery. A simulated universe simulates how the real universe might be. Our results suggest that no technological advancement will make the simulation hypothesis in any universe that works like ours. Will make the simulation hypothesis possible in any universe that works like ours. So if there's a universe like ours, like we will never be able to simulate a universe like ours. We will never be able to simulate a planet like ours with full fidelity. However, the limitations outlined above might be circumvented if the values of some of the fundamental constants involved in our formalisms are radically different than the canonical values they have in this universe. Saying anything remotely consistent about the different physics operating in any other universe is an impossible task, and let alone to guess which combinations of constants would still allow the development of any form of intelligent life. Nevertheless, just for the sake of argument, we can make the very bold assumption that in each of explored variations, some sort of intelligent life can form, and that it will be interested in computing and simulations. Under this assumption, we can then explore numerical changes to the values of fundamental constants involved in the previous modeling, see whether combinations exist which can make at least a low resolution of our planet doable with a limited use of time and energy. So in a final plot twist whose irony should not be missed, now this universe, which might be a simulation, attempts to Monte Carlo simulate how the real universe out there could be, in order for the simulation of this universe to be possible. That is kind of funny. We assume that all known physical laws involved in our formalism are valid in all universes, but we allow each of the key fundamental constants to randomly vary across realizations. For the sake of the exercise, we shall fix the total amount of information required for the low-resolution simulation of our planet discussed in section 3.3, and consider the Hawking temperature relative to the black hole which is needed in each universe to perform the simulation. The simulation consists in a Monte Carlo exploration of the 6-dimensional parameter space of the fundamental constants, which entered our previous derivation. So they're going to allow 6 different parameters to vary. So 6 different constants of nature to vary, and then maybe they can get a more reasonable... Maybe they can prove that, or maybe they can show that there is some universe, some possible universe, that can simulate our universe more efficiently. From 10 to the 6th randomly drawn universes, we select all realizations in which the low-resolution simulation of our planet is possible. Each constant is let free to randomly vary across 40 orders of magnitude, Jesus Christ, around its reference value. Our simplistic definition for possibility for the simulation here stems from 2 conditions. So what they're telling us is that they need to... they're basically going to tell you what they mean by a possible simulation. So the simulation should run at least in real time or faster than real time in the universe where the simulation is produced. This means that a time interval of 1 second in this universe is simulated in the equivalent of 1 second in the real universe. However, any other universe can have different evolutionary timescales than this one depending on their age. By considering that 1 second is 10 to the minus 18th universe times, we require that 1 second of this universe can be simulated in 10 to the minus 18th universe times of computing time in any other universe. To easily compute the universe time, we assume for simplicity Einstein de Sitter cosmology in every other universe, and hence the universe time is 2 over 3 times h, where h is the Hubble-Lemaitre constant of the other universes. So they're basically saying the simulation has to run fast enough. And then we need to talk about power consumption. The used power to produce the simulation should be reasonable. How can we guess what reasonable would be in any other universe? We cannot, of course. But for the sake of the exercise, we use 1 gigawatt of power as a goal. This is about the power provided by a modern nuclear reactor, and it is 100 to 1,000 times higher than the typical power consumed by the best high-performance computing center to date. Thus, it represents some extreme power budget available to numerical astrophysicists of the remote future. In the previous case, we must scale this power for the properties of other universes, and to do that, we consider that 1 gigawatt equates to 6.6 times 10 to the 18th protons converted into energy in a second, where for the second we use the normalization of the previous step. Therefore, we assume that in any other universe there are planets or something conceptually equivalent, and that a very tiny fraction of their mass can be used to support computing. So, 10 to the minus 33, 1 in 10 to the minus 33 of the mass of the Earth. No, they are deep pockets. They already considered quantum computing. Quantum computing doesn't help you here. We give in Figure 1 the results of the Monte Carlo simulation, in which we show sampling of the distribution of allowed combinations of constants normalized to the value each of them has in this universe. Although the exploration of the full 6-dimensional parameter space is complex, a few things can be noticed already. First, 2 well-correlated parameters here are c and h. For a given value of the age of the universe, the computing time scale as h over th, which is the Hawking radiation temperature. So if c increases, the Hawking radiation temperature of the black hole increases, lowering the computing time scale, while at the same time proportionally larger values of h are allowed. Another couple of correlated constants is the speed of light and the gravitational constant. H was the Planck constant, by the way, which stems from the condition on the power. From this condition, it follows that the speed of light cubed divided by the gravitational constant is proportional to the mass of the proton. Hence, an order of magnitude of increase in c must be compensated by a 3 orders of magnitude increase in g for a fixed value of the mass of the proton. Most of the other combinations of constants show instead lacks of obvious correlation. We'll finish reading this paragraph and then we'll go look at the data. In general, this simulation shows that combinations of parameters exist to make this simulation hypothesis for a low-resolution version of planet Earth possible, and similarly also for a higher-resolution version of the simulation hypothesis, although they require orders of magnitude in difference compared to the physical constants of this universe. It clearly is beyond the goal of this work to further elaborate if some of the many possible combinations make sense based on known physics, if they can support life, and whether the hypothetical forms of life will be interested in numerics and physics as we are. The full direct simulation of such cases, possibly down to the resolutions at which conscious entities will emerge out of the simulation and start questioning whether their universe is real or simulated, is left as a trivial exercise to the reader. LMAO. All right, let's look at the data. So, what they find, so what do we want? So the red, so there's more allowed universes in the red. So, yeah, so if the speed of light is like 15 orders of magnitude bigger than it is in our universe, and Planck's constant is 30 orders of magnitude bigger in our universe, and if the gravitational constant is 30 orders of magnitude greater, and if the Hubble constant is 10 orders of magnitude smaller, and the mass of the proton is 30 orders of magnitude higher, then maybe they could simulate our universe. Who would have thought? Okay. Okay, so what about this last section? What if the universe performing in the simulation is entirely different than our universe? That's a reasonable question. Why don't you go live with Parker anymore? Oh, because I haven't been doing politics stuff, and that's all he's been doing. If he ever goes back to doing more philosophical stuff or science stuff, I'm happy to do it, but he just does politics now, so... Right. Guessing how conservation laws for energy and information applies in a universe with entirely different laws, or whether they should even apply in the first place, appears impossible, and this entirely prevents us from guessing whether the simulation hypothesis is possible in such a case. For example, hypothetical conscious creatures in the famous Pac-Man video game in the 80s will just be incapable of figuring out the constraints in the universe in which their reality is being simulated, even based on all the information they can gather around them. They would not guess the existence of gravity, for example. They would probably measure energy costs in power pellets. This guy's a jokester. And they would not conceive the existence of a third dimension, or of an expanding spacetime, and so on. Even if they could ever realize the level of graininess of their reality and make the correct hypothesis of living in a simulation, they would never guess how the real universe, our universe, if it is real indeed, functions in a physical sense. In this respect, our modeling shows that the simulation hypothesis can be reasonably well tested only with respect to universes which are at least playing according to the physics playbook, while everything else appears beyond the bounds of falsifiability and even theoretical speculation. All right, let's read the conclusion. We use standard physical laws to test whether this universe, or some low-resolution version of it, can be the product of numerical simulation, as in the popular simulation hypothesis. Our first key result is that the simulation hypothesis has plenty of physical constraints to fulfill, because any computation is bound to obey physics. We report that such constraints are so demanding that all plausible approaches tested in this work in order to reproduce at least a fraction of the reality we humans experience require the access to impossibly large amounts of energy or computing power. We are confident that this conclusively shows the impossibility of a matrix scenario for the simulation hypothesis, in which our reality is a simulation produced by future descendants, machines, or any other intelligent beings in a universe which exactly is at the one we think we live in, a scenario famously featured in the Matrix movie in 1999, among many others. We showed that this hypothesis is just incompatible with all known laws of physics, down to scales which have been already robustly explored by telescopes, high-energy particle colliders, or other direct experiments on Earth. What if our reality is instead the product of a simulation in which physical laws, e.g. fundamental constants, are different than in the reality that we're used to? A second result of this work is that even in this alienating scenario, we can still robustly constrain the range of physical constants allowed in the reality simulating us. In this sense, the strong physical link between computing and energy also offers a fascinating way to connect hypothetical different levels of reality, each one playing according to the same physical rules. In our extreme simplistic Monte Carlo scan of models with different fundamental constants, a plethora of combinations seem to exist, although we do not dare to guess which ones could be compatible with stable universes, the formation of planets, and the further emergence of intelligent life. The important point is that each of such solutions implies universes entirely different from this one. Finally, the question whether universes with entirely different sets of physical laws or dimensionalities could produce our universe as a simulation seems to be entirely outside of what is scientifically testable, even in theory. This is to say, all the people who say, oh, they have different physical laws than us. Well, then you're just prescribing magic. Like, it's not even in principle testable. And so, like, we shouldn't consider it. It's not even in principle conceptualizable, right? At this point, we shall notice that a possible simulation hypothesis, which does not pose obvious constraints on computing, might be the solipsistic scenario in which the simulation simulates just the single activity of the reader's brain. That's me, while all the rest is a sophisticated and very detailed hallucination. In this sense, nothing is new from René Descartes' evil genius or Deus Deceptor, i.e., for some reason, an entire universe is produced in a sort of simulation just to constantly fool us. From its more modern version of Boltzmann brains. Conversely, a more contrived scenario in which the simulation simulates only the brain activity of a single individual appear to quickly run into the limitations of the simulation hypothesis explored in this work. A shared and consistent experience of reality requires a consistent simulated model of the world, which quickly escalates into a too demanding model of planet Earth down to very small scales as soon as physical experiments are involved. So even if it was just simulating all of the humans that are conscious, you still run into the same issue, because there are physicists who are conscious who are probing, very, very small parts of the universe. This is funny. A possibility for such models to work may be that all scientists actually are similar to non-playable characters in video games, i.e. roughly sketched and unconscious parts of the simulation playing a pre-scripted role, in this case reporting about fake measurements. So it could be that I'm an NPC. Maybe. At this fascinating crossroad between physics, computing, and philosophy, it is interesting to notice that the last egotistic version of the simulation hypothesis appears particularly hard to test or debunk with physics, as the latter appears to be entirely relying on the concept of a reality external to the observing subject, be it a real or a simulated one. However, the possibility of a quantitative exercise like the one attempted here also shows that the power of physics is otherwise immense, as even the most outlandish and extreme proposal about a reality must fall within the range of what physics can investigate, test, and debunk. Luckily, even in the way most probable scenario of all, the universe is not a simulation, the amount of mysteries for physics to investigate still appeared so immense that even dropping this fascinating one cannot make science any less interesting. That's a nice closing. Then there's some conflict of interest and acknowledgements and all of this lovely stuff. Fascinating paper. So, what's the takeaway? Well, the takeaway is, if you're going to make the simulation hypothesis, and keep in mind, the simulation hypothesis is predicated on the idea that, we will eventually make simulations that are somewhat like us. Like, we make simulations where there are people and gravity and things like this, like that's what GTA 6 is. The simulation hypothesis goes that if we would make simulations like us, then it could be that we would be the simulation of somebody else like us. But if they're like us, that means that they're in the same laws, that they have similar laws of physics as ours. Which means that it's impossible. It can't be the case, unless you're just proposing that some crazy alien is simulating humans for some reason. And why would they do that? There's no reason to think that that would be the case. The only reason anybody even takes the simulation hypothesis seriously is because we might be interested in simulating humans. But we wouldn't be interested in simulating just anything. It would be specifically, perhaps not humans, but things that are like our universe. Why would we simulate a universe with completely different physical laws? So this is all to say, I am going to be referring to this paper in the future when talking about people who believe in the simulation hypothesis, because it basically debunks the whole argument. So everybody, that is all I have for you today. A lovely paper about the simulation hypothesis. Fascinating read. If you want to read it, or if you want to follow along, this will be on YouTube. You can go rewatch it later, or you can go read the paper, which is in the background here. You can just pull it up. It's freely available online. It came out 4 days ago. With that said, thank you guys all for being here. Thank you to Grimlock and for those who have supported me. And I will see you guys tomorrow.